In this video, you're going to be learning about radioactive decay, and it's a form of absolute dating, so we need to discuss what absolute dating is first. You have already studied relative dating, and basically we took a look at rock layers and we decided which is the oldest, which is the youngest, or how old are they relative to each other. But in absolute dating, it's really more about coming up with a number or an exact age of the rock. And we can accomplish that through radioactive dating. It's also called radiometric dating. And it's based on the regular radioactive decay of certain elements. And you can find this table on the front page of your Earth Science reference table, and it lists the 4 radioactive isotopes that we're going to be concerned with this year in Earth Science. And it also lists what it will decay into, or the daughter product that will be created. So for example, carbon-14 will decay into N14, and it also gives us the half-life, or the amount of time it's going to take for half of that carbon-14 to decay into N14. So radioactive elements are unstable. They're going to decay or change over time into other elements. So we talked about this just a little bit, that carbon-14 will decay into N14. Potassium-40 will decay into either argon or calcium. So this chart is going to list what the radioactive isotope is and what the daughter product is, or what it will decay into. The half-life of an element is the time it takes for half of the material you started with to decay or to change into something else. So if we go back to carbon here, remember carbon-14 will decay into N14, and this is the half-life. So 5.7 times 10 to the third. We can also say 5,700 years. That's how long it takes for half of the amount of carbon found in a sample to decay or change into nitrogen-14. So an example, if I had 20 grams of carbon-14 in a sample, after 5,700 years goes by, I would have 10 grams of carbon-14 and 10 grams of nitrogen-14, because half of the carbon would have changed into nitrogen in this amount of time. And we'll do some practice with that, so it'll sink in a little bit for you. Each element has its own half-life, and those half-lives are constant. They're not going to change, no matter how much we have. So if we look, each of these elements has a different half-life that is characteristic for that element. So if we take a very simplistic example, there's a make-believe radioactive isotope called popcornium, and it has a half-life of 100 years. So if there are 16 popcorniums right here, in this 100 years, half of them will turn into something else. So let's take a look. Okay, so 8 of those 16 have changed into the daughter product, and that would have taken 100 years, because that's what the half-life is. So if another 100 years goes by, I'm going to cut the number of popcornium I have left in half again. So if there's 8 here, 4 will change into something else in the next 100 years. So I would say this sample now is 200 years old, because 2 half-lives have went by, and I've cut the number of popcornium in half twice. So if another half-life goes by, I will cut the 4 that are left in half again. So now this sample would be 300 years old. If another half-life goes by, I'll cut the number I have left in half again. So I now have 1 left, and another half-life has went by. So if another half-life goes by, it doesn't mean that this goes away altogether. What ends up happening is that it's cut in half again. So what I would actually end up with is half of this is the new product and half is still the daughter product. If another half-life goes by, I cut this in half again. So it just keeps getting smaller and smaller and smaller and smaller, but it never fully goes away. So let's take a look at a little bit more realistic example. So this box right here represents a piece of bone that contains carbon-14. So we have that little section of the Earth Science reference table up here that tells us what the half-life is and what the daughter product is of carbon-14. So right now we're going to say that this organism has just died. So the bone is brand new. It has 100% of the carbon-14 it's ever going to have at this point in time. So our white boxes are going to represent carbon-14, and blue boxes will represent the amount of N14. So at 0 half-lives, this organism just died. We have 100% of the carbon-14, 0% N14, and the age is 0. So after 1 half-life goes by, remember that's 5,700 years, half of the carbon, or 50%, has decayed into N14, and 50% is still carbon-14. It shows down in our chart down at the bottom, and the age is 5,700 years. If another half-life goes by, we cut that carbon-14 in half again. So we now have 25% carbon-14 and 75% N14. And the age is 11,400 years because we add the 2 half-lives together. Another half-life goes by, another 5,700 years, and we've cut that remaining carbon-14 in half again. So we now have 12.5% carbon-14, 87.5% N14, and the age of this bone is now 17,100 years. That's 3 half-lives. Okay, if another half-life goes by, we cut this in half one more time, and we now have 6.25% carbon-14, 93.75% N14, and 22,800 years old the sample is. Okay, so each time we're cutting this number in half, in half, in half, and we're adding whatever we cut from this to this number. So it was 100%. We cut it in half, it's now 50%, so there has to be 50%, that's now N14. If I cut the 50% in half again, it's 25%. Well, I cut 25% off, so that has to now be N14. Let's take a look at another example. So if I have a piece of rock that contains uranium-238, here's the half-life of uranium-238, 4.5 times 10 to the 9th years. So again, here's my key. The white boxes are uranium-238, and the blue boxes are Pb-206. So at 0 half-lives, I have 16 grams, right, represented by the 16 boxes of uranium, and 0 grams of lead. And the age of this rock is 0. The rock is just formed. It has the maximum amount of uranium it's going to have ever. So if 1 half-life goes by, 4.5 times 10 to the 9th years, I'm going to cut that 16 grams in half. So I should have 8 grams. So let's see that. So 4.5 times 10 to the 9th years goes by, and I have half lead and half uranium. So I have 8 grams of lead and 8 grams of uranium. And the age of the sample is 4.5 times 10 to the 9th years. Another half-life goes by. I now have 4 grams of uranium and 12 grams of lead. So you see I cut this 8 in half to 4. So I took 4 and it changed, so I have to add the 4 over to the lead. And now the age of the sample is 9.0 times 10 to the 9th years because 2 half-life have went by. Another half-life goes by, I cut it in half again. So I now have 2 grams of uranium and 14 grams of lead. And the age of my sample is 1.35 times 10 to the 10th. If you're confused at all about scientific notation, ask us for a little mini lesson and we'll go over why it's 10 to the 10th and not 13.5 times 10 to the 9th. Another half-life goes by, that's another 4.5 times 10 to the 9th years, and that means that my sample is cut in half again. I now have 1 gram of uranium-238 and 15 grams of lead, and my sample is 1.8 times 10 to the 10th years old. Now, if I keep going with this, remember, this 1 gram does not become 0. This would become 0.5, and I would then add 0.5 over here because it just keeps getting smaller and smaller and smaller. It never fully goes away. We just keep cutting it in half and in half and in half. So let's solve a typical problem you might see on a Regents exam. The diagram below represents the present number of decayed and undecayed atoms in a sample that was originally 100% radioactive material. So they're not starting you at the very beginning with the sample. They're saying some time has went by and it used to be 100% undecayed, but now we have a mixture of decayed and undecayed. So it wants you to figure out really kind of how old is this sample. So they're giving you the half-life of the radioactive material, that's 500 years, and they want to know what is the age of the sample represented in the diagram. So in this diagram, you're actually going to have to work backwards a little bit. So if we were to count up these boxes, these atoms, there are 32 total atoms. So that tells us 32 were once undecayed. It said it was 100% undecayed at one point. So 32 were once undecayed. So I need to figure out, how did I get from 32 to where I am now? So I need to know how many decayed and how many undecayed do I have. We now have 8 undecayed and 24 decayed atoms. So if I start with 32, after one half-life, that number would be reduced by half. So I would have 16 undecayed and 16 decayed. Well, I know I don't have that. I have fewer undecayed than that. So I know that I actually need to cut it in half again. So after 2 half-lives, the number of undecayed would be cut in half again, and I would have 8 undecayed and 24 decayed. And that's exactly where I'm at right now. That's what the diagram shows me. So now I know that 2 half-lives have went by. Well, if each half-life is 500 years and 2 have went by, that means my sample is now 1,000 years old. And that would be my answer.